In electrocyclic reactions, a conjugated pi system, so like you have here, alternating double and single bonds, double, single, double, single, double. That conjugated pi system, the electrons in it move around to create a ring. So you have the electrons in a conjugated pi system moving around to create a ring. So these are called electrocyclic reactions. Now, there are a lot of different ways that can happen. Now, specifically, there's 8. Let's organize them a little bit. Notice that all these reactions on the left are happening to just 2 conjugated pi bonds. So in all of these starting materials, you have 2 pi bonds that are conjugated in all 4 of these examples. So that's on the left. On the right, we have 3 conjugated pi bonds. So double, single, double, single, double, conjugated, and we have 3 pi bonds. And that's the case for everything on the right. So you want to organize these electrocyclic reactions in your head first based on whether they're happening to 2 conjugated pi bonds or 3 conjugated pi bonds. And the second thing you want to look for is whether you're using heat, as in the case on the top here, or whether you're using light. That's what that H nu, that V is actually the Greek letter nu, and it means frequency. H nu is just a shorthand for light. So that's what we have on the bottom here. So first, do you only have 2 conjugated pi bonds, or do you have 3? And second, are you doing the reaction with heat, or are you doing it with light? And knowing those 2 things will narrow down what your predicted product would be. But notice in all of these cases, you're starting with a chain that's just a straight chain, and you're ending up with a ring. Starting with a chain that's just a straight chain, and you're ending up with a ring because of the way that the electrons move. These are all electrocyclic reactions. So this is just that same information on that last slide, but this time it's in table form. So you have the 2 conjugated pi bonds, the 3 conjugated pi bonds, heat and light, and here you have how the branches are coming off of the straight chain before it forms a ring. So for example, here the branch is going up and then down at the 2 ends, and so that would be like up, down. Here you can see the branches going down, and you can see down and down. Also, if it were up and up, you'd get the same answer. So you look at how the branches are coming off at the ends, and then you can use this table to figure out how the branches will be once you form the ring. So for example, if you're using heat on a 2 conjugated pi system, the branches should be, and the branches are going up and down at the end of the conjugated pi system, then they're going to be trans in the product, in the ring that you form. So let's go through these one by one and see why they're happening. What is really happening to create this trans or cis configuration when these electrocyclic reactions form rings. So if you have 2 conjugated pi bonds, then that's going to happen because you have a p orbital on each of these carbons that has a double bond on it. So you'd have 1, 2, 3, 4 p orbitals. And that's what you're seeing over here. And this can split into different waves. This now, remember that each of these p orbitals is a standing wave. And when they're right next to each other, they can combine to form molecular orbitals. A p orbital is an atomic orbital. It tells you how an electron flies over just one atom. But when you line them up like this, they all overlap. And now the electron isn't just flying around one atom, it's able to fly around the whole molecule. So these are called molecular orbitals, and they're a wave pattern, a standing wave, that the electron can move in around the whole molecule. As the wave increases in energy, you get more and more of these nodes. You'll see an example of that in a separate video. I'm sure before the videos for the Diels-Alder reaction, you can see an example of why you get nodes when the waves become more energetic, or of how you get those nodes when the waves become more energetic. But every time the wave pattern gets a little more energetic, you get one more node. So you start it with none. These are all in phase, all have blue at the top, all have red at the bottom. As you go up, you get one node. The nodes are always produced symmetrically, so this one node is right in the middle. So you have 2 blue, and then it switches to 2 red. These colors are representing the phases of the wave. A 2-dimensional wave has up and down. These 3-dimensional waves are not just occurring in 2 dimensions, so it's not just up and down, so they use colors to represent the wave phase. And so you get this one node in between here for this next molecular orbital. In the next most energetic molecular orbital, so notice as you go up, the energy is increasing. The next most energetic molecular orbital has 2 nodes, and it's symmetrical, so this is the only way you'd have that. And as you go up one more, you get 3 nodes, and so they switch every time. So red to blue, that's 1 node, blue to red, a 2nd node, red to blue, a 3rd node. So these are the different waves that electrons can move in when they fly over 4 atoms, when they fly over this conjugated pi system. Now, only 2 electrons can fit in each orbital because they act like little magnets. So one can go up with its north side up, the other can go down with its north side down. But if you tried to stuff another one in there, the north side would either have to go up or down, and the electrons that are already there would repel it. So only 2 electrons can fit into each of these waves, these molecular orbitals. And because we have 2 pi bonds, there are 2 electrons in each one, we have a total of 2 plus 2, or 4. So we'll put 2 in the bottom wave pattern and 2 in the next highest one. And so now we have this second molecular orbital from the bottom that is the highest occupied molecular orbital. And it's the wave patterns at the end of that that are going to contribute to the way that these bonds have to turn to create the ring. So to understand how you get how you would predict the product for this, you have to think about how this highest occupied molecular orbital would behave. And for that, you can look at the following demonstration.
So what I have here is the highest occupied molecular orbital for butadiene, 1,3-butadiene, when it's only being exposed to heat. So there's just this one node right in the middle where the phase, which is here represented by blue, switches to the other phase of the wave, the standing wave, here represented by green. And on the end here I have 2 red atoms that are supposed to represent branches. So if you have branches coming off of this 1,3-butadiene, and one of them is going up and the other one is going down, when these molecular orbitals, when the bonds rotate to allow the molecular orbitals to overlap, you'll notice that one of the branches goes up, the other goes down, and so you have a trans arrangement of those branches in the new ring that you form. So one more time, you're like this. In order to get those orbitals to overlap, the 2 branches move so that it's trans. They're trans to each other in the new ring.
So you can see that if you have 2 conjugated pi bonds, as in 1,3-butadiene, if you have 2 conjugated pi bonds and the branches coming off of the conjugated system, the carbons coming off of the conjugated system, if one is going up and the other one's going down, and you're using heat, then you'll get a product that's trans. Now this plus En means it's plus the enantiomer, so that would be if this top one were coming out at you, so a solid wedge, and the bottom one were going away from you, so a dashed wedge. That changes the handedness, whether the right hand or left hand, R or S, for each of these 2 chiral centers. And so you'd get, if you changed both of those, you'd get the enantiomer. And you can get both, you would get both of the enantiomers when you do this electrocyclic reaction. So that's why they have the plus En. And so in the table, that was represented by this first case. You're using heat. The branches off of the end of the conjugated system are going up and down, and we only had 2 conjugated pi bonds, so it was trans. Here, similar case scenario, we have 2 conjugated pi bonds, so 1, 2 pi bonds that are conjugated. But here the branches are going in the same direction. This top one is going down, and the bottom one is also going down. We're still doing the reaction in the presence of heat, and so you'll see how that affects the ring in the following.
So here's a model of the highest occupied molecular orbital for 1,3-butadiene. It has just the one node going down the middle, where the phase of one wave, here represented by blue, switches to the opposite phase, here represented by green, of that standing wave. And in this example, I have the two branches coming off of the ends of the benzene, both going in the same direction. So you could see either here they're both going down, or if you were to move the molecule, you could say they're both going up. So either way, they're going in the same direction. This red one is clearly going up, the other red one is slanted, but it is also going up. It's not just to the side. So if you have that arrangement, when the single bonds rotate, in order to allow for the molecular orbitals to overlap, you can see that the branches move so that they're both on the same side. So in that case, they would be cis. So one more time. You start out with this highest occupied molecular orbital, and if those single bonds rotate, in order to allow overlap of those two green molecular orbitals that are in phase, you can see that the branches become cis. So you see it rotating, the branches become cis.
So we saw how if you're using heat, your highest occupied molecular orbital looks like this. And when those rotate to overlap with each other, if the branches at the end of the conjugated system, if one is going down and the other is going down, or if they're both going up, they're both in the same direction, then when they form the ring, they're going to be cis to each other on that ring. And so in the table, that was the second case. So we're still looking at two conjugated pi systems. The branches are going in the same direction, and we're using heat, so cis. Now, if you use light, something different happens. Here, if you use light, one of these red electrons here, when the light hits the molecule, that one of those electrons starts flying in a different way, and it jumps up to this next wave pattern, this next molecular orbital. The way that the light hits it, the electron, and when it flies more in a more energetic way, that energy is expressed as a more energetic wave. And more energetic waves have these more nodes, like this one here. So light hits the molecule, and one of these electrons jumps up, and now this here, the psi3, that is the highest occupied molecular orbital. And notice that the phases of the wave has changed at the ends. On the ends here, they were out of phase, but now the ends are in phase. And so that affects the type of product you get. To visualize the type of product you get, you can see this following video.
This is a model for the highest occupied molecular orbital for 1,3-butadiene when it's exposed to light. You've seen the highest occupied molecular orbital when it's exposed to heat. That only had one node. When the light hits the molecule, it makes one of the electrons start flying around faster. And that makes it fly around, it shifts it to this higher energy wave pattern for the molecular orbitals. And you can tell it's higher energy because in this example, you don't just have one node, you have two. There's a node in between these carbons where the phase in one direction, represented by the green, switches to the phase in the other direction, represented by the blue. So that's one node. And there's another node on the other side where the phase represented by blue switches to the phase represented by green. So you have these two nodes there representing a higher wave pattern. So this, because the light shot the electron into a new, more energetic molecular orbital, you get this more energetic molecular orbital as the highest occupied molecular orbital for 1,3-butadiene when it's exposed to light. Now in this example, I have two red atoms. Those are representing branches. And notice if you look at it from the side, one is going up and the other is going down. So if you have that pattern of branches on your and you're exposing 1,3-butadiene to light, when those molecular orbitals on the 1,3-butadiene rotate so that they overlap, you can see that those branches now are going in the same direction. They're both going up in that new ring that you're forming. They're both going up, and because of that, they are considered cis. So, one more time. You have one branch going up, one branch going down. For 1,3-butadiene, when it's exposed to light, when the molecular orbitals overlap, the branches twist to be going cis.
So if you use light on a two conjugated pi bond system, and where the carbons coming off the ends of that system are going in opposite directions, one up and one down, then you'll end up getting a cis product. And that is represented in this third row on this table here. We're using light that changes the highest occupied molecular orbital. If the branches at the end of the conjugated system are going in opposite directions, one's going up, the other one's going down, and you only have two conjugated pi bonds, then you'll end up with the branches coming off as cis in the ring that you form. If the two carbon chains coming off of the conjugated pi system are going in the same direction, so like these red ones here are both going down, also if they were both going up, and you're using light again, so the electron jumps up to this next highest wave pattern, then the rotation of the molecular of the bonds to give you proper overlap of the molecular orbital results in a different product. You can see the product that you'll get in this next video here.
So here we have again the highest occupied molecular orbital for 1,3-butadiene when it's exposed to light. It has those two nodes, one where green shifts to blue at the top, one where blue shifts to green at the top. And those two nodes are representing the higher energy wave pattern that the most energetic electron is moving in this molecule when it's exposed to light. And the difference here between the last example is that here the two branches are going in the same direction. So either you can say they're both going down, so this one's going down and the other red atom is going down, or if you look at it the other way, you could imagine them both going up. So this one's going up, the other one is going up. So when you have that scenario, when you have that type of branches coming off of a 1,3-butadiene that's exposed to light, so it has this as its highest occupied molecular orbital, when those bonds rotate, in order to allow the molecular orbitals to overlap and create the new bond in the ring, notice that the branches are trans. So one more time, if you take this highest occupied molecular orbital for 1,3-butadiene when it's exposed to light, and you rotate it so that the molecular orbitals overlap, the branches rotate so that you get the trans version of the branches coming off of the rings. So that trans arrangement is coming from the overlap of the end of the molecular orbitals, the phases at the end of the molecular orbitals when it's linear, those having to twist to overlap.
So if you have two conjugated pi bonds, a system of two conjugated pi bonds, the branches are going in the same direction, and you're using light and the highest occupied molecular orbital that goes with it, and then you'll get a product in your ring. You'll get a product that is trans. Now, each of these are chiral centers. There's no preference for one chiral center over the other, so you'll get a 50-50 racemic mixture of both this one and its enantiomer, where this top methyl group would be coming out at you, and the bottom methyl group would be a dashed wedge representing that it's going away from you. And so that's what they're talking about down here. You have two conjugated pi bonds in a system, and the carbons coming off of the ends of it are going in the same direction, either both up or both down. Then in the ring that you form, those branches will be trans. Okay, so much for two conjugated pi bonds. You can see we've thought through all of those. Now let's go on to three conjugated pi bond systems. Now if you have three conjugated pi bonds, like here, double, single, double, so conjugated, and we have 1, 2, 3 pi bonds. If you have three conjugated pi bond systems, each of the carbons in these double bonds have p orbitals on them. So you'd have 1, 2, 3, 4, 5, 6 p orbitals. And so you can see those 6 p orbitals over here. Now, those are all going to merge, and electrons are going to be able to fly as waves over that entire space. But the wave will travel differently depending on how much energy it has. At the lowest amount of energy, the wave will look like this. It'll travel like that. It's a three-dimensional standing wave. It looks like that. As it gets a little more energetic, you'd have the one node. Remember, you had nodes one at a time, and they're always symmetrical. As it gets even more energetic, you'll have two nodes, and you add them in so they're symmetrical. As the electrons move even more energetically through that space, they would travel as a wave with four nodes. And so they would look like this. As the electrons travel in that space even more energetically, they'd have another node. So now they'd have four nodes. And finally, at the very top, the most energetic way that the electrons could fly over that space, those 6 atoms, is if they had 5 nodes. That would be a very energetic wave, standing wave pattern. So this 3 pi system, there are 2 electrons in each of the pi bonds, so we have 2, 4, 6 pi electrons total that we need to fit into these wave patterns. Only 2 electrons can fit into each wave pattern, so you'd fit 2 in the bottom one, now that's full, 2 in the next highest one, now that's full, and your last 2 will go in your third highest molecular orbital. So this orbital right here, psi 3, that's the highest occupied molecular orbital for a 3 pi conjugated system. So if you take that molecular orbital, it's the ends of that orbital trying to overlap, turning to overlap correctly, that allows you to predict what the product of this reaction would be. And you can see that in the following video.
So I have here the highest occupied molecular orbital for 135 hexatriene when it's only being exposed to heat. So we have our 6 carbons here. You can count those black balls. Those are carbons, so we've got 6 carbons. And here in the highest occupied molecular orbital, when the molecule is only exposed to heat, you have 2 nodes. So your first node is in between the blue and the green phases. Those are different phases of waves, opposite phases of waves. Your first node is right there, and your second node is between this next green and blue phase here. So you sort of have 2 blues, 2 greens, 2 blues. That's the highest occupied molecular orbital for 135 hexatriene when it's exposed to heat. At the ends of this conjugated system, I have 2 branches, and those are in red. Now if you look at it from the side, you can see that this is kind of what it would look more like on a piece of paper. You can see that the 2 branches are going in opposite directions. So one of the red ones is kind of going up, the other red one is kind of going down. So they're going in opposite directions. Now if 135 hexatriene, or any molecule with 3 conjugated pi bonds, only 3 conjugated pi bonds, is exposed to heat only, then you'll have this as your highest occupied molecular orbital. And when the bonds rotate to allow the molecular orbitals at the end of that system to overlap, you'll notice that in the ring that you get, the 2 branches, the red atoms here, are on the same side. So here they're both going down, or if you look at it the other way, they're both going up. So if you take that 6-membered ring, so you take that 6-membered ring with the 2 nodes, so the highest occupied molecular orbital for 135 hexatriene, and you rotate the ends so that those orbitals overlap in the same phase, so they add together to create that new bond in the ring. The 2 red branches here, whatever branches were coming off of those 2 carbons, are on the same side of each other. They're on the same side of the ring. They're going in the same direction, so they would be cis. So if you just use heat with 135 hexatriene, and you have branches, 2 branches that are going in opposite directions, so one up and one down, they're going to overlap, the orbitals will overlap to give you a cis product at the end there.
So you can see that if you have 3 conjugated pi bonds and the carbon chains coming off of the ends of those are going in opposite directions, then when the bonds rotate to allow for overlap, the correct overlap of the ends of the molecular orbital, that will form a ring where those carbon chains are cis. And so that's just summarized in this video, in this table in word form. So again, if you're using heat and you have 3 conjugated pi bonds and the branches off of the end of the conjugated system are going in opposite directions, you'll end up with the branches as cis on the ring that you form. Now, if the branches are going in the same direction, so for example here they're both going up at the ends of the system, at the ends of the conjugated system, then you can use this highest occupied molecular orbital here with the 2 nodes to predict what those branches will be like after you form the ring, as you can see in the following video.
So here again we have the highest occupied molecular orbital for a 1,3,5 hexatriene, or just 3 conjugated pi bonds. It has 2 nodes. So the first node is right here, where the blue is on top is shifting to the green wave version on top. And then notice if you follow along, it shifts again. You go from the green wave to the blue wave again. These are opposite ends, opposite phases of the wave. They would cancel each other out if they met, but here they're just traveling as a node. So this is the pattern of molecular orbitals that you have, the pattern for the molecular orbital that you have, the highest occupied molecular orbital for 1,3,5 hexatriene. Now, on the molecule, I have the branches so that they're going in the same direction. You can see this red one is going up. The red branch at the bottom is also going up. So when you take that molecule and it rotates so that the molecular orbitals overlap, you can see that these 2 branches are going in opposite directions. The red one here on the right is going up and the red one on the left is going down. So when you take the lowest occupied, molecular orbital for a 3 pi bond conjugated system, like 1,3,5 hexatriene, you take that lowest the highest occupied molecular orbital for that system when it's only exposed to heat, and it'll rotate to give you branches that are going in the trans configuration in that new ring that you make.
So if you're using heat so that this 3rd highest energy wave pattern is your highest occupied molecular orbital, then, and the 2 branches the 2 carbon chains at the end of the conjugated system are going in the same direction, then you'll end up with those branches being trans in the ring that you form. And these are both chiral centers. There's no preference, there's no reason why this center, either of these centers should be only one hand, the right or the left hand, R or S. And so you'll get a mixture of compounds. You'll get this compound where one is R and one is S, and then you'll get the enantiomer where the chiral centers switch configurations, and you'll have a 50-50 mixture of that. And the name for a 50-50 mixture is just a racemic, R-A-C-E-M-I-C, racemic mixture. And so that's just the same information summarized in this table form. You have the 3 conjugated pi bonds. You're using heat. That lets you know what your highest molecular orbital is. The branches at the end of the conjugated system were going in the same direction, so when they formed a ring, they became trans. Now, if you use light, a similar thing happens with a 3 conjugated pi bond system as happened with a 2 conjugated pi bond system. When the light hits the molecule, it gives its energy to one of these electrons. And now the electron starts moving in a more energetic way. The electron is moving as a wave, and the higher energy wave is going to be expressed as having more nodes. The direction of the wave will shift more often. And so we had 2 nodes before. When you irradiate this with light, the electron jumps up to the next higher way of moving. And now you get this new orbital here, this new molecular orbital as your highest occupied molecular orbital. It's occupied now because an electron is in it because the light pushed it there. So this is your new highest occupied molecular orbital. And so the phases at the end of one side stayed the same, but at the end of the other side changed. And so the way that the bonds are going to have to rotate to get these ends to overlap and form a sigma bond is going to be different. And that's going to leave you with branches pointing in different directions when you form the ring. So to predict how these branches are going to be arranged in space, in other words, to predict the stereoisomerism of these two branches when you form the ring, we're going to use this new highest occupied molecular orbital because of the light, and you can predict it using that as in the following video.
I have here the highest occupied molecular orbital for a 3 pi bond conjugated system, like 1,3,5-hexatriene. I have the highest occupied molecular orbital here when it's being irradiated with light. So when you hit 1,3,5-hexatriene with light, the light shoots the electron up to the next highest molecular orbital. And so you have this here. Now that next highest molecular orbital has more nodes than the lower orbital where the electron was before the light hit it. And so you'll notice that this has not just the number of nodes that we saw for the thermal, it has one more. You have one node here, it changes 2 nodes, here's our second node, and then our third node here. So this has 3 nodes, whereas in the case of 1,3,5-hexatriene that was only exposed to heat, there were only 2 nodes. So here we have 3 nodes. This is a higher energy molecular orbital, but because we're irradiating the molecule with light, an electron jumps up and starts flying around in this way, in this pattern, in this wave pattern across the molecule. And I have here 2 branches that are in red, and here they're going in opposite directions. So one is going down, one is going up. So you can see that if you have the highest occupied molecular orbital for 1,3,5-hexatriene, you have the highest occupied molecular orbital for 1,3,5-hexatriene that's being irradiated but with light, then when the ends of the molecular orbital rotate so that they overlap in phase with each other, you end up with your branches, those red atoms, being trans. So, one more time, you start with the highest occupied molecular orbital for 1,3,5-hexatriene when it's exposed to light, and when the chain, which there's no branch at the bottom, there's no bond at the bottom there, you're going to form that bond by rotating these molecular orbitals, and when you do that, the 2 branches go in opposite directions, so they are trans.
So when you have that 3 conjugated pi system, and you're using light, and the branches at the end of it are going in opposite directions, then you end up getting the trans product. And as we've seen before, anytime you get this trans product, these are chiral centers. There's no preference for one chiral center over the other, so you get a mixture, a 50-50 racemic mixture of the 2 enantiomers. And this is just that same information summarized in word form. You've got the 3 conjugated pi bonds. You're using light, so that changes your highest occupied molecular orbital. So now it rotates in a different way in order to get the orbitals to overlap. And the 2 branches coming off of the end of the conjugated system, which were going in opposite directions, are trans in the ring that you form. This is the same sort of scenario. You're still using 3 conjugated pi bonds. That's your system. And you're still using light, so the electron is jumping up to the next highest wave pattern, and that's going to be the highest occupied molecular orbital now. But the difference here is that the 2 carbons that are coming, the 2 branches that are coming off of the ends of the conjugated system are going in the same direction. So they're both going up here. And so when they rotate, you can predict when the bonds rotate in order to allow the ends of this highest occupied molecular orbital to overlap and form a new sigma bond. These carbon chains rotate, and you can predict their arrangement in the ring that you'll form. They're in 3D space, as in the following video.
So here again I have the molecular orbital, the highest occupied molecular orbital for 135-hexatriene that's being hit with light. When the light hits the molecule, it makes one of the electrons flying around in the highest occupied molecular orbital jump up to the next highest occupied molecular orbital. It starts moving around as a more energetic wave, and that more energetic wave is described by this pattern, which has 1, 2, 3 nodes. And so these colors are representing waves. In a two-dimensional wave, it would be going up and going down, but these are three-dimensional waves, so they're just opposite phases of the waves, these colors. And the nodes, but you get more nodes between them, the more energy that the wave is expressing. So here, your highest occupied molecular orbital now is like this if you have 135-hexatriene being hit with light. And so when this comes together, you don't have a bond at the bottom. Notice that I have the red branches here going in the same direction, so you could either say they're both going down, or if you put it the other way, it looks like they're both kind of going up. If they're in the same direction, either both down or both up, then when these bonds rotate, in order to allow the molecular orbitals to overlap, the two branches go in the same direction. So this new bond here, that I'm pressing together with my fingers, that's a new sigma bond that you're making. And when that happens, in order for that to happen, the atoms have to rotate in such a way as to make these two branches both go down. So if you have, a 135-hexatriene that you're hitting with light, and the branches start out both going in the same direction, then when the bonds rotate to allow for the formation of that new bond, the branches you have will both be going in the same direction. They will be cis on the new ring that you have.
So if you have a 3-conjugated pi system that you're irradiating with light in order to make the electron jump up to move in a new highest occupied molecular orbital, that's going to rotate, and here's two branches coming off of the end of that system are going in the same direction, then the bonds are going to rotate in such a way as to give you a cis product there. And so that's just summarized as in word form in this table. And so now we have summarized all the different 8 scenarios that we originally saw and the reason behind them. All of these are arising because of waves, standing wave patterns that are traversing large sections of the molecule. In other words, they're happening because the phases in molecular orbitals at the ends of conjugated systems are overlapping. And that's turning what were pi bonds into sigma bonds. And it's changing the position of the other pi bonds. So we'll use this table in future problems, but it's in this video that we derived and explained where these patterns are coming from.